Namaste dosto. Imagine you are playing with a hula hoop or drawing a big circle on the ground. Now, if you pick any 2 points on that circle and join them with a straight stick or chalk line, that line is called a chord. Simply put, a chord is a line segment whose endpoints lie on the circumference of a circle. Here's something interesting. This chord divides the circle into two parts, which we call arcs. Think of it like slicing a pizza slice from the whole round pizza, creating two curved edges. Now, imagine you stand or mark a point somewhere on the circle and then connect both ends of the chord to this point. The shape you get in between these lines is an angle. We say this angle is subtended by the chord at that point. For example, if you have chord AB and a point C on the same circle, then the angle CB is the angle subtended by chord AB at point C. But here's the fun part. The size of this angle depends on where point C is placed on the circle in relation to the chord AB. This idea is really important because it helps us understand why some angles are the same, and also leads us into the fascinating world of cyclic quadrilaterals where all corners lie on one circle. Let's begin with a beautiful theorem about circles. The theorem says, equal chords of a circle subtend equal angles at any point on the same side of the chords. Imagine a circle where we have two chords, AB and CD, and both are equal in length. Now, if we take a point P on the circle and join AP and BP, and similarly join CP and DP, the angles formed at P are equal. In other words, if chord AB equals chord CD, then the angle APB equals angle CPD. This happens because the triangles APB and CPD are congruent. Both have equal sides since the radii of the circle are the same and the chords are equal. This property is very useful when we deal with equal arcs, sectors, or any symmetrical constructions in circle geometry. Now, let's explore one of the most famous circle theorems, the relationship between the angle at the center and the angle at the circumference. Take a chord AB in a circle with center O. This chord makes an angle at the center. Let's call it angle AOB. And it also makes another angle at a point C on the circumference. Angle is CB. The theorem states that the angle at the center is always twice the angle at the circumference when both are subtended by the same chord. So we can say angle AOB equals 2 times angle ACB. This rule helps us find unknown angles in circles easily. Whether the point lies on the major arc or the minor arc, the relation always holds true. Let's apply this rule to a simple example. Suppose a chord AB subtends an angle of 60 degrees at the center of the circle. We need to find the angle it subtends at a point C on the circle. By the theorem we just learned, angle CB equals half of angle AOB, substitute the values. Angle CB equals 1/2 multiplied by 60 degrees. That gives us angle CB equals 30 degrees. So the angle subtended at any point on the circumference is exactly half the angle at the center. Here comes a special and very famous case, the Thales Theorem. It says, the diameter of a circle always subtends a right angle at any point on the circle. So, if AB is a diameter and point C lies anywhere on the semicircle, then angle CB equals 90 degrees. That means triangle ABC is a right-angled triangle. This property is often used in geometry constructions, and it even connects directly to the Pythagoras theorem, since every triangle drawn on a diameter is a right triangle. Let's wrap up the concept with a quick summary. Formula 1. Angle at the center equals 2 times the angle at the circumference when both are subtended by the same chord or arc. Formula 2. Equal chords subtend equal angles on the same side of the circle. Formula 3. A diameter subtends a right angle, that is 90 degrees at any point on the semicircle. In short, remember these 3 key ideas. The angle depends on where the point lies, equal chords behave symmetrically, and a diameter always gives a perfect right angle.